Hello friends, I am Dr. Sangeeta Patil, Assistant Professor in the Department of Electrical and Electronics Engineering, MIT School of Computing, MIT ADT University. Welcome you all for a course on basics of transformer. Let us start the lecture. So, here we will study the two tests which are carried out on a transformer. These two tests are independent tests and the data obtained from these two tests are jointly used for finding out the efficiency and regulation of the transformer. So let us see the first test, that is the open circuit test. Open circuit test is also called as OC test on the transformer. So here I have drawn the experimental diagram or circuit diagram for carrying out the open circuit test on the transformer. So this is your transformer. This one is your transformer. Just I will write down here. This is a step down transformer on which I am going to perform the open circuit test. So this is your primary of the transformer and this is the secondary of the transformer. As the secondary turns are less than the primary turns, this transformer is a step down transformer. So in OC test, the primary of your transformer is connected across suitable AC supply. So this is your AC supply. Let us give this is phase, neutral. This is your suitable single phase AC supply. So the primary of this transformer is connected across suitable AC supply through one ammeter as AC supply. This is your AC ammeter, voltmeter. So let us draw one voltmeter here. So this is a voltmeter which is again AC voltmeter. So ammeter, voltmeter, and this is your wattmeter. Wattmeter has four terminals. This is your main, line, common and voltage. So this is a wattmeter. Let W is the reading of this wattmeter. So this ammeter, voltmeter and wattmeter is connected in the primary circuit. The secondary of the transformer, as name itself indicate, it is an open circuit test. So secondary of the transformer is kept open. However, if you have to determine the turns ratio of the transformer, then you have to connect one voltmeter across the secondary. So this is again one voltmeter. If you kept normally open this secondary winding of the transformer open, then it is also okay. But if you have to determine the turns ratio of the transformer, then we have to connect one voltmeter across the secondary, right? Because what is there? The resistance of the voltmeter being very high, your secondary is just regarded as a open circuit without any load when we connect the voltmeter across the secondary. So the connecting voltmeter across the secondary is as good as of the open circuit because your internal resistance of voltmeter is very high. In actual practice, students, the low voltage side is preferred for giving the supply from safety and convenience point of view. Also, sometimes high voltage supply may not be available for testing purposes. So, it is preferred to give suitable AC supply to the low voltage side of the transformer. Then let us see what is the procedure for the performing the open circuit test. So, in open circuit test, we have to adjust the voltage across primary to its rated value. Suppose this transformer is 230 by 110 volt. I am taking just example. Then what is the voltage rating of the primary? 230. What is the voltage rating of the secondary? 110, right? So I have just said that while performing the open circuit test, we have to give supply to the low voltage winding, but in our lab 230 volt is available. That's why I have connected 230 volt side to the 230 volt winding of this transformer to the single phase AC supply, right? So in this test, what we have to do, we have to apply the rated voltage across the primary of the transformer. So for applying the rated voltage of the primary, we have used the variac, which is also called as a auto transformer, So a variac or suitable arrangement we have to make for adjusting the rated value of the voltage across the primary. Then after that we have to make the following observations by taking the reading. So let us see what is the observation table of this. So after adjusting the voltage across primary to its rated value, the readings of various instruments that we have to record as shown in the observation table. So this is your serial number. Here I will write down the primary side reading, and on this side I will write down this as a secondary side reading. So on primary side we have connected one voltmeter, ammeter and wattmeter. As I have conducted the open circuit test, there is no load connected across secondary. So I will denote the voltage across primary as a V1. Then after that, the whole current through the primary winding is the no load current, which is denoted by I0, and the power which is taken from the supply on the no load is W0. On secondary side, there is no current, only voltage is there. So on secondary side, just I will rub this. On secondary side, what we have to do? We have to take only the voltage reading. V2. So as shown in the observation table, we have to record the readings of various instruments. Those are connected on the primary side and the secondary side. So later this is only one reading we have to take. What is the rated voltage of the transformer? It is 230 volt as I have shown here. So it will be 230 volt only. Then we have to note down what is the current taken by your primary winding or the transformer on the no load, and W0, what is the power taken from the supply to overcome the no load losses. Then let us see what calculations we can do from the open circuit test. So let us see calculations and results. Okay, so the ratio of now why I have connected voltmeter across the secondary, because I have to calculate the turns ratio. Students, we know that V1 upon V2 is equal to N1 upon N2, and what is your N1 upon N2 is nothing but the turns ratio. So as you have recorded the voltage across secondary, the ratio of your voltmeter readings V1 by V2 will give you the turns ratio, accurately give you the turns ratio. The magnitude of your no load current I0 gives the check on the magnetic quality of the iron core and the joints. It will give you the magnetic quality of iron core and joints. If you remember students, we have studied that if your magnetic core is made up of the silicon steel which is having higher permeability, then very less current or negligible current is required to set up the flux in the transformer. So the quality of your iron core and joints depends upon your no load current value. So your no load current gives a check on the magnetic quality of the iron core and the joints. If your no load current is less, means the material which is used for the iron core and the joints, it is good in the quality. So very less current is required to set up the flux. Then the reading of W0. The reading of W0 gives you iron loss of the transformer. Iron loss of the transformer. Remember students, second side circuit is not closed. So no current will flow through the secondary side. Only current will flow on the primary side, which is denoted by this ammeter which is connected on the primary side. So this is your no load current. So no load losses will take place. What are the no load losses? Those are nothing but your iron losses. Iron losses means hysteresis loss and eddy current loss. Also very small or negligible copper loss will take place in the primary winding, right? So the primary winding copper loss, that is I square R loss of the primary under this condition is negligible because our I0 is very small. So the copper loss is negligible. So my W0 will indicate the iron loss of the transformer. Then now come to the equivalent circuit of your transformer referred to the primary side. Come to the, this is your V1 voltage applied. This is the current taken from the supply, which is nothing but vector sum of I0 and the I2 dash. I2 dash. Now what is I2 dash? As there is no load connected across this secondary, this is V2 dash is nothing but secondary voltage referred to the primary side. So my I2 dash, as there is no load connected across the secondary, my I2 dash will be 0. My I2 dash will be 0. What is this? This is R0. This is X0. What is current through this? This is your IC and this is core loss component of your no load current, and this is the magnetizing component of your no load current. So the values of R0 and X0 of the shunt circuit. Why this shunt circuit we have included in the equivalent circuit? For accounting for your no load current. So the values of R0 and X0 of shunt circuit accounting for no load current can also be calculated from the data which is obtained from the open circuit test on the transformer. So this figure gives you the equivalent circuit of transformer referred to primary side. Let us, I will write down here. This is referred to primary side. Okay, so from this reading, what are the readings that we have? We have V1, we have I0 and we have W0. Okay, so from these three readings, let us see what we can calculate. Okay, so what we can calculate the no load power factor. We can calculate the no load power factor. Let that power factor is denoted by cos of phi 0. So how to find out the no load power factor? See, what is your W0? W0 we can write down in single phase power. What is the formula for single phase power? Vi cos of phi. So what is voltage on primary side? V1. What is current on the primary side? I0. The angle between V1 and I0 is nothing but cos of phi 0. So I can write down V1 I1 cos of phi 0. As we know W0, V1 and I0, from this I can find out the no load power factor, which is nothing but ratio of no load power and the product of primary voltage and the no load current, right? So this is the one calculation that you have to do from the readings that you obtain from the no load test. This is your equation number 1. Right? Now from no load phasor diagram we have seen what is your I naught is vector sum of what? Im is along this axis, x axis, because we have taken flux as in, then Ic is in phase with the E naught in opposition to that of your E naught. So this is your Ic, and vector sum of your Ic and I naught is nothing but, it is nothing but I naught. So vector sum of these two is nothing but your I naught. So this is your I naught. Right? And V will come along this axis. V will come along this axis. Only we have seen this. Right? So what is angle between V and I naught is nothing but, this angle will be phi 0. So from this phasor diagram that we have learned previously, I can write down my IC is equal to I0 cos of phi 0. I0 cos of phi 0. Similarly, I can write down Im is equal to I0 sin of phi 0. I0 sin of phi 0. All these are in amperes. Please write down the units. Okay. Hence, referring to the equivalent circuit which is I have drawn above, refer to the primary side. What is my R0? From this I can write down, from this figure, what is the voltage across R0? V1. Right? So V1 divided by IC. How I have calculated IC? IC is nothing but I naught cos of phi 0. So V1 divided by IC, I can find out I0. Similarly, what is voltage across X0 is nothing but the V1. So V1 divided by Im will give me the X0. So from OC test, we can determine the parameters of the shunt circuit. Right? So referring to the equivalent circuit, we can write down R0 is equal to V1 upon IC. How to find out IC? From equation number 2. From equation number 2. So we'll get the new equation. This is in Ohm. Equation number 4. Similarly, I can write down my X0 which is equals to V1 divided by Im or I magnetizing Ohm again. Right? So we can find out the parameters of the shunt circuit. That shunt circuit is included in the equivalent circuit to take into account the effect of the no load current. Or alternatively, we can also write down, in some books it is find out in another way. Alternatively, I can write down R0 equals to V1 square upon W0. Because we know what is power. Power is equal to V square upon R. Right? So, R I can write down V square upon the power. So, what is the power in our case? W0. So, which implies that I will write down R is equal to V square upon P. Means ratio of voltage square upon P. So, what is the voltage? In our case, V square upon what is the power in the primary? W0. So, I can find out by this method also. Right? Then, what is IC? Then after finding out I0, I can find out IC. What is IC is nothing but V1 upon R0. So alternatively, you can go by this method. It is in ampere. It is in ampere. Then after finding out IC, we can find what is your I0? I0 is nothing but under root of Im square plus IC square. So after getting IC, you can find out IM because you have I not reading. IM equals to under root of I0 square minus IC square. Right? After finding out IC, we can find out the XM. We can find out the XM. What is XM? Will be nothing but V1 upon IM. V1 upon IM. So you can use any method for finding out the parameters of the shunt circuit by using the open circuit test data. By using the open circuit test data. I hope all of you understood the open circuit test. Now let us see the short circuit test on the transformer. So let us draw the experimental setup or circuit diagram for the short circuit test. Name itself indicates we have to short circuit the secondary. So in this method, your primary is connected across the suitable variable low voltage AC supply through an ammeter, voltmeter. Let us draw one voltmeter on this side. So let us, this is your voltmeter and this one is your wattmeter. This one is your wattmeter. So my primary is connected across a suitable variable low voltage AC supply through an ammeter, voltmeter and the wattmeter as shown in the figure. This is your primary, right? And this is your secondary. And secondary terminals we have to short circuit. And secondary terminals we have to short circuit using a link of negligible resistance. It is a link of negligible resistance. Why negligible resistance? Because we know that current always follow the path of least resistance. It is just like a short circuit. So secondary terminals are shorted solidly using the link of negligible resistance. The current on high voltage side of transformer being less, we know that Ohm's law is not applicable for the transformer because my power P in is approximately equals to P out. What is your P in? V1 I1 cos of phi 1, right? Equals to what is P out? V2 I2 cos of phi 2. Cos of phi 1 and cos of phi 2 both are approximately equal for the transformer. So I can write down V1 I1 equals to V2 I2. So V1 upon V2 equals to I2 upon I1, means voltage and current both are inversely proportional to each other in case of the transformer. So on high voltage side your current will be less and on the low voltage side your current will be more. So the current on the high voltage side of the transformer being less, it is always convenient for us to connect the high voltage side to the supply and the low voltage side should be short circuited. So remember one thing, always you have to short circuit the low voltage side and you have to give voltage on the high voltage side, right? So again I will repeat it, as the current on the high voltage side of the transformer is less, it is always convenient to connect the high voltage side to the supply and we have to short circuit the low voltage side. Then voltage applied across the primary winding we have to adjust such that it will circulate the full load current in the primary and secondary circuit. So this will indicate my I1 full load and this will indicate my I2 full load. you can short circuit this secondary by means of the ammeter also, right? So students, just again I will repeat what I have to do. I have to increase the voltage across primary, or I have to apply the voltage across primary winding till the ammeter in the primary circuit will indicate its full load current, right? Means it ammeter will indicate the full load rated current of the primary. When your ammeter indicate the full load rated current of the primary, at that time we have to note down the various observation in the tabular format. So let us see what we have to note down. So again I will write down serial number here. On primary side, what reading we have to take, and on secondary side, what reading we have to take. So as we have not connected anything on the secondary side, you don't have to note down any reading on the secondary side. So this is not applicable. But on the primary side, we have to find out what is the voltage which is required to circulate the rated current of the primary circuit, and that voltage is denoted by VSC, short circuited voltage. Then this is primary short circuit current, and this is your primary short circuit power, WSC. So these readings we have to record in the tabular format. Since a very small voltage is required for circulating the full load currents in both the winding, that is primary and the secondary, we have to take the precaution while applying this voltage, right? Very small voltage is required to circulate the rated current. So that voltage we have to increase in step with the help of this variac or the auto transformer. So here this variac, by means of this variac, we have to increase the voltage till this ammeter will indicate the rated current of your primary. If the voltage exceeds this value, then your winding may get damaged due to overheating by heavy circulating current. So if this VSC will go beyond its value, then this I1 will go beyond this value. This current, short circuited current, will go beyond its value. So the primary winding which is carrying the current more than that is rated value, as well as secondary carrying the current more than that of its rated value, at that time overheating may take place, and due to overheating the insulation which is used in the transformer, that may get burned out. Okay, so due to heavy circulating current, the insulation or winding may get damaged. Then now let us see what calculation we can do with the help of these readings. So what readings we have? VSC, ISC and WSC. So let us see what are the calculations and results that we will get from the short circuit test. Let us see. The current in both the windings being the full load current, the wattmeter reading gives us the full load copper loss of the transformer, right? As the full load currents are flowing through the circuit, means your WSC will give me the full load copper loss. Full load copper loss, right? Voltage applied across the primary winding of the transformer is very small. So the flux density in the transformer core is also small, right? Voltage applied across the primary during short circuit test is very small. Therefore, flux density will be small. Flux density will be small, and hence the iron loss of the transformer under this condition is approximately equals to 0 in comparison to the copper loss. And due to some difficulty, if the short circuit test is conducted with the currents which are other than the full load currents in the primary and the secondary winding of the transformer, corresponding to full load copper loss, corresponding to that your full load copper loss can be calculated by remembering that your copper loss is proportional to the square of the current. So here, as we have neglected the PI, my WSC will give me the full load copper loss. Full load copper loss. Now let us see what is the equivalent circuit referred to the primary side. So this is the equivalent circuit referred to primary side. Now, how it will get modified for the short circuit test? Students, the equivalent circuit of the transformer referred to primary side under short circuit that will get modified. Applied voltage is very small. So let us, this is your VSC. This is your VSC. So the applied voltage is very small under short circuit condition. The current component I0 is negligible. As the applied voltage is very small, the current I0 is negligible in comparison to the load component of the primary current, right? That's why what I will do, I will omit the shunt circuit which is consisting of R0 and X0. So just I will remove this circuit from the equivalent circuit. Why we have to omit this? Because under short circuit condition, the applied voltage VSC is very small, which is required to circulate the full load current through the primary and the secondary. So, as the applied voltage is very small, the current component, primary has two components. Primary current is vector sum of your I0 and I2 dash. So, I0 is negligible in comparison with the load component of your primary current because your VSC is very small. Hence, the shunt circuit which is consisting of R0 and X0, I have totally omitted from this equivalent circuit. Now, what is this? This is your RT1. What is RT1? Total resistance of the transformer referred to the primary side. And this is your XT1. Total reactance of the transformer referred to the primary side. And this is your short circuiting link. Because we are performing the short circuit test. So this is your short circuiting link. So now, firstly we will find out RT1 from this. So what is WSC? What is WSC? WSC is nothing but copper loss. Just I have explained. Copper loss because full load currents are flowing and in comparison to your, as your no load current is very small, voltage required to circulate the full load current is very small, your I0 is very small, we have neglected the iron loss. So WSC will give you the copper loss, full load copper loss at full load because full load currents are circulating. So I can write down WSC is equal to ISC square into RT1. From this equivalent circuit, I can write down WSC is nothing but ISC square into RT1, right? Watts. So what is your, you have recorded WSC, you have recorded ISC. So what is RT1 is nothing but WSC upon ISC whole square. This is your equation number 1. So the total effective impedance of the transformer, that also we can find out which is referred to the primary side. So you have, what is your ZT1? Total impedance of the transformer referred to primary side is nothing but RT1 plus J XT1, right? So the total effective impedance, that is ZT1 of the transformer referred to primary side, can also calculated from the reading by using the formula VSC upon ISC. Because we know V divided by I is nothing but Z in the AC circuit. So simply taking the ratio of VSC to ISC, we will get the ZSC. So ZT1, that is the total effective impedance of the transformer referred to the primary side. Then you have RT1, you have ZT1, you can find out the XT1. So what is XT1? XT1 will be under root of ZT1 square minus RT1 square. RT1 square. Again you will get this in ohm. Right? It is very important, students, here to note that when the primary is short circuited and the supply is given to the secondary, all the data will also belong to the secondary side in that case. Then the constant of your equivalent circuit calculated from this data will be obviously referred to the secondary side only, right? So in that case, if you are drawing equivalent circuit, refer to the secondary side and you are applying the voltage to the secondary and you are short circuiting the primary, at that time your WSC is nothing but ISC square into RT2, right? Then ZT2 will be VSC upon ISC. VSC upon ISC. Then you can find out XT2 is equal to under root of ZT2 square minus RT2 square. So these are the formulas. If you are short circuiting the primary and applying voltage to secondary, and in that case you have to draw the equivalent circuit referred to the secondary side only, because you are applying voltage to the secondary. Then at that time, what is your RT2? Total effective resistance of the transformer referred to secondary side. So WSC will give you the ISC square into RT2. Then from this you can find out RT2. From this we can find out RT2. What is RT2 will be WSC upon ISC whole square. So constants RT2, XT2, ZT2 can be then find out by referring the circuit to the primary or referring circuit to the secondary side. Then how to now, what is our interest? Our interest is in finding out the efficiency and regulation of the transformer, right? So let us see now the calculation of efficiency from OC and SC tests. We know what is the input power. Input power in watts on the open circuit test Means when you have performed the open circuit test on the transformer, what is the input power? W0. And that W0 is nothing but your iron loss. Iron loss, which is denoted by PR. And input power in watts on the short circuit test will be equals to WSC, and that WSC we have taken as a full load copper loss. Full load copper loss, which is called as PCU full load. PCU full load. Right? So, then what is the total loss of the transformer? Total loss of transformer we will get equals to PI plus PCU. So, it will be W0 plus WSC. Then we know what is efficiency at full load. Percentage efficiency at full load will be equals to full load output in watts divided by full load output in watts plus W0 plus WSC, means iron loss and the copper loss at full load into 100. Now, what is full load output in watt? How to find out that? We can find out that by, we know students, one relationship. What is your KVA? KVA is nothing but kW into upon cos of phi. If the KVA of the transformer is known, if I multiply that KVA by cos of phi, I will get the KW. What is KW? Is nothing but the output of the transformer. So above formula I can modify as percentage efficiency at full load equals to full load KVA rating it is in obviously volt ampere into power factor divided by full load rating in VA volt ampere into power factor. I mean this will be full load output. So for this I am substituting. KVA into power factor is nothing but the output in watts plus iron loss is nothing but W0, copper loss at full load is nothing but WSC into 100. So if the KVA rating of the transformer is given to you, then convert that KVA into volt ampere by multiplying it by 1000 multiplied by power factor so that you will get the output in kW. This is the efficiency at the full load. But the efficiency at any other load can be find out also. So the efficiency at any other load, say X into full load is desired. Suppose Suppose the efficiency at any other load, say x into full load, is desired in any problem, then what is the copper loss? Then what is the copper loss? Then I can write down, then the copper loss at x into full load equals to x square into copper loss at full load. Why? Because copper loss is proportional to current square, right? Copper loss is proportional to current square. So this I can write down as x square into WSC, because my WSC is giving me the full load copper loss. So your efficiency formula will get changed. So percentage efficiency at x into full load. What is x? X is nothing but the fraction at which you have to find out the efficiency. Suppose I am saying I have to find out efficiency at 50% of load. Then this x will be 0.5. X will be 0.5. So efficiency at x% of load is nothing but it will be given by x into full load rating, x into full load rating in VA into power factor. So kVA into power factor will give you the output in kW, right? Divided by, again I will write down here, x into full load rating in volt ampere into power factor plus iron loss is constant throughout. So W0 I will write down as it is, and your copper loss will change as a square of that fraction. So x square into WSC into 100. So you can find out the efficiency at any fraction of the load. Suppose it is mentioned in the problem that find out the efficiency at 75% of the load. Then what is your x? Your x should be 0.75. So for finding out the output at 75% of load, what we have to do? You have to convert the kVA into volt ampere multiplied by power factor, so that you will get the full load output of the transformer multiplied by that fraction. Means that will be the output of the transformer at that fraction, right? So find out the output of your transformer at that fraction. So x into full load rating of your transformer in volt ampere into power factor. So this will be your kW. kVA into power factor will be kW into x, means kW at that fraction. So this will give you the output at that particular fraction. Then in the denominator, output at that fraction plus iron loss plus copper loss at that fraction is nothing but x square into WSC, right? So in this way we can find out the efficiency of the transformer. So student, it should be remembered that at 25% of load, the value of x will be 0.25. At 50% of the load, value of x will be 0.5. And at 75% of the load, the value of x will be 0.75, and so on and so on. So the factor x is sometimes called as degree of the loading. X is nothing but called as degree of loading, means how much load you are putting on the transformer. So it is also called as degree of loading. Then calculation of the regulation. So as we have referred equivalent circuit refer to the primary side, we can use directly the formula. Percentage regulation, this we have seen in the last lecture. Percentage regulation equals to I1 RT1 cos of phi plus minus I1 XT1 sin of phi divided by V1. What is V1? Rated voltage of the primary. What is I1? Rated full load current of the primary. What is RT1? RT1 is the total effective resistance of the transformer referred to primary side. From which test you will get this? From the short circuit test. Cos of phi at a desired power factor you can find out the regulation. Similarly, XT1 you will get from the short circuit test. So this formula you have to use for finding out the regulation. And students, in this way we can use combinedly or jointly the data which is obtained from the OCSC test performed on the transformer to calculate the efficiency and regulation of the transformer, right? So in this formula your XT1 RT1 you have to take from the short circuit test, and V1 is rated voltage of the primary, I1 and I2 are the full load primary and secondary current respectively, right? So this is all about the mathematical expression that is required for finding out the efficiency and regulation of the transformer using the open circuit and short circuit test data. So in next lecture we will see some problems for finding out the efficiency and regulation of the transformer. So thank you for your patience listening. If you like this lecture, if you like this video, please don't forget to like, share and subscribe my YouTube channel. Thank you once again students. Thank you.